pronouns. It's a joint name with Tomáš Gavenčák, which is a student of Jan and Sangelholm. And I want to talk about properties, deciding first order properties, but before that, let me do some motivation. So, all of us know that if we want to decide monadic second order logic properties on graphs, that's the famous theorem of Bruno-Purcell from 1990, I believe. And this theorem says you can do so if you have bounded tree in an FPT way, and the FPT way means linear time. So I promised to talk about matroids, and there's an extension of this result to matroids. So I will define what a matroid is in a second. And this is due to Petr Hliněný, who as I was, he was a student of Jan, so he's my academic brother, and he proved in 2003. So the result is a little bit added, but it got published only in 2003, that you can decide in cubic time, so again in FPT, but here you will have an assumption of bounded branch width, which is a parameter which is closely related to tree width. You can define it for graph, but somehow for matroids it's more natural to work with bounded branch width. And you need one more thing, you need representability over a fixed finite field. So let me draw that here. So I probably should define what a matroid is. There are several definitions of matroids. So what is a matroid? So it's a generalization of the concept of linear independence, and you have a pair x and y. The elements of x usually are called just elements of matroids, and I is the set of independent sets, or family of independent sets. And they should satisfy some axioms. So first of all, an empty set is independent, I is hereditary, meaning that if y is in I and y prime is a subset of y, when y prime is also in I. And the last axiom, which is the most important axiom, is an analog of the axiom for the basis in linear spaces. And if you have two sets, let's say y and y prime from I, and let's say the first one is smaller than the second one, when there exists an element of the bigger one, but you can add to the smaller one, and the set will be independent. So we have examples. As I said, this notion should generalize the concept of linear independence of vectors over finite fields. So an example is if X is a set of vectors over a field, and I are subsets of linearly independent vectors from X, when this pair forms a matroid. And we also say that if, so it's not true that whenever you have a matroid you can find a representation of it over some field. So it's not true that any matroid is isomorphic to a matroid that can be obtained in this way. Matroids that can be, they are isomorphic to some matroid that can be obtained in this way are called representable. And if you want to specify, you can say it's representable over some field, meaning like the vectors that you're taking are the vectors over that field. And if you mount the graph theory side, which probably has a majority of the audience, and another example is that X, you take the edges of a graph, And now we have two choices. The more canonical one are subsets, spanning or yielding acyclic subgraphs. So these are edges that do form four-raster subgraphs in the original graph. And it is well known that matroids that are obtained in this way are representable over any field. So such matroids are representable over any field. And matroids that are representable over any field are called regular. And another way of obtaining a matroid from a graph is not taking edges, subsets of edges with your acyclic subgraph, but what you can also do, you can take subsets of edges whose removal does not increase the number of components. And such matroids that can be obtained in this way are called cographic, and they are also regular. They are also representable over any field. And actually, if you have a planar graph, and you start with this matroid and you take the dual of the planar graph in the usual planar way, that means you replace the row of faces and vertices. When the matroid of the new graph that would be obtained in this way is isomorphic to the matroid of the original graph that you can get in this way. So what Peter did, he proved that if you have a matroid representable over a fixed finite field, maybe let's say over the two-element field, over the binary field, it has a bounded range with, and you can decide any monadic second-order logic property in cubic time. So maybe I should say a little bit more about this assumption of the representability of over finite fields. So it seems somehow to be necessary in the result. And first of all, there's a negative result of Peter from 2006, that if you take matroids representable over the rationals, when when it's NP hard to test whether the matroid is binary, and there's an even earlier result of Seymour, where if you would put here no condition on the representability, when deciding whether a matroid of branching free is binary, you cannot do in sub-exponential time in the Oracle model, and that's an unconditional result. So somehow there's some result that you really need representability over finite fields, and also this is kind of consistent with the general belief and the recent work of Gielen, Kral, and Whittle, or that they obtained the analog of the graph minor series for matroids representable over finite fields. So somehow this class of matroid is closer to the graph, so it's not so surprising that you can prove results or analog of subscript. So as it was announced in the title, I should be speaking about first order logic properties. And in the first order logic, where of course it's easy to design a polynomial time algorithm for a fixed order, first order logic property, well you just, so maybe I should briefly recall that first order logic property. So we remember from the previous talk what monadic second order logic properties are. In the first order logic property, you can quantify only over the element. So essentially you have something where x is a vertex, such that for every edge where x is our free vertices, and then you have some formula. So of course such a formula you can decide in polynomial time. Simply you can try all the possibilities. The hard thing here is to design FPT algorithm. And there are plenty of theorems. I will just put maybe the first one, which I believe for one, I should check my notes, which was kind of the more general one, and this was Frick and Groh, and they proved almost linear time By that I mean for every epsilon an algorithm running in time n to 1 plus epsilon for graphs that have something we call locally bounded G-width. So I will define this, and there have been several generalizations I will briefly mention in a minute. So, what does locally bounded G-width means? So we say that a class of graphs, so it's not a property of a graph. The tree-width is a parameter of a single graph. Locally bounded tree-width is a property of a class of graphs. So a class of graphs has locally bounded tree-width if the following is true, where x is a function such that for every graph from the class and every vertex of this graph, the vertices, and for every d, the vertices of G at distance at most d from V induce a subgraph of tree-width at most the function of d. So what do you want? So you want a function that for your class of graphs bounds the tree-width of the subgraphs induced by closed neighborhoods, by the vertex, its neighbors, and the neighbors of its neighbors, and so on. This bound, of course, depends on how many vertices you take, but you want one function which universally bounds this for all the graphs in your class. So an example, one particular example, are planar graphs. And it's kind of intuitive, and if you look at a planar graph, and let's say you take neighbors at distance at most 3, and somehow if you swap like this, you obtain kind of a circular-like decomposition from which you can make a decomposition as it appears in path. So actually you can prove that the path is bounded by...
No. On the tree, basically.
On the tree? Oh, okay. So path. Yeah, right, of course. Yeah. But basically this is kind of the basic idea. And when there has been several generalizations, so I just throw in some name. There has been a generalization of Davar, Grohe, and Kreutzer. And again, you have been an FPT algorithm for graphs locally excluding a minor. And these are graphs such that for every d you have a fixed graph that does not appear as a minor in any subgraph induced by vertices at distance d from any vertex in any graph that appears in the class. And the most general result is or another generalization due to Zdeněk, myself, and Robin Thomas. Another proof was obtained by Davar and Kreutzer, and this is for graphs with locally bounded expansion. And bounded classes of graphs with bounded expansion. This is a notion defined by Jarek Neshetřil and Patrice Osona de Mendes, and where you include graphs, proper minor classes of graphs and many others, but unfortunately I don't think I have a time to define it here, so I just wanted to mention this example. So what was our work? So we started at filling this part of the table, and what we can prove here. So our result. So instead of bounded branch width, we have locally bounded branch width. And immediately you should jump on me and ask me what do I mean by locally, because I have no notion of distance in a Matroid, and I explain it in a second. And instead of representability over a finite field, we need a little bit stronger assumption of the Matroid being regular, and when we have an FPT algorithm. So I should first comment on the regularity here, and the regularity seems somewhat important because there are some results from the codes that testing the existence of a circuit of a given length is probably is W1 hard for binary Matroids, so it's somewhat unlikely that you can weaken this condition of regularity too much. So let me define what I mean by locally bounded branch width. So again, it's a property of a class of Matroids. And the key thing is that I should tell you what I will mean by the distance of two elements in the Matroid. So, and the distance between E and F will be defined as the minimum of C, where the minimum ranges over all circuit C of a Matroid containing both E and F. So I don't want to define what a circuit in a Matroid is. If you're not familiar with Matroids, then just think of graphs and cycles in graphs. So I want to say that two elements are close if they lie on a short common cycle. And when I analogously define that locally bounded branch width, that X is a function, that for every Matroid from the class, the submatroid, which is M, every D, every element of M, the submatroid restricted to F, such that the distance between E and F is at most D, and this Matroid has branch width at most F. So the nice property is that if G is a class of graphs with locally bounded branch width, tree width, when the corresponding class of graphic Matroids obtained in this way has locally bounded branch width. But the converse implication is not true. So you can have a class of graphs that do not have locally bounded tree width, but if you jump to the corresponding graphic Matroid, when the class will have locally bounded branch width. But this is the implication you want to have, because this tells you that it's a generalization of frequent graph horizon. So in the remaining 5 minutes, I want to say a few words about how we proved, or what are the hard things that we have to cope with. So surprisingly, the hard thing was not to design the FPT algorithm, but was somewhat easy. So what we do, we construct a guide point graph, and two elements in guide point graph are adjacent if they lie on a common short cycle, where the wet short is defined with respect to the formula. So if you have a formula with 10 variables, then you have to consider longer cycles than if you have a formula where the quantification is just over 3 elements. And the hard thing was actually to decide whether two elements lie on a common circuit and when to be able to construct the Geifman graph. Because once you have the Geifman graph and you use Geifman's theorem, it basically tells you that deciding first order logic property is equivalent to deciding first order logic formula with locally restricted quantification, and for when you basically apply the machinery developed by Frigg and Grohe in their paper, and when you can do everything. And you need also to apply the Liani's result to decide the properties on Matroids we found it. So the hard thing is to decide. So the hard thing, hard in the sense it was hard to find the algorithm, but it's not hard in the sense there would not be an algorithm. So there is an FPT algorithm. Where the parameter is D, which decides whether for an input regular Matroid. So recall that the Matroid is regular with representable over any field. Whether two given elements lie on a short cycle, on a circuit of length at most. So this was the hardest part of our paper, and for this we use the following ingredients again and again. I will just flash in some verse. So first of all, the structure of regular Matroids is known. So well known. So there's a seamless decomposition theorem. Which tells you that every regular Matroid can be obtained from graphic Matroids, co-graphic Matroids, and one particular Matroid on 10 elements by gluing along small cuts. So essentially, what you can think, if you're a graph theorist, that you start with your graph, and what you can do, you can glue two graphs on an edge or on a triangle. So this is basically what this theorem says, except instead of only taking graphs, you have to take co-graphic Matroids, which are Matroids of this form, and another Matroid on 10 elements. So this kind of suggests that you should solve this problem on graphs, you should solve this problem on this kind of duals of graphs, and on one particular 10 element thing. So 10 element thing from the algorithmic point of view is easy. Solving this problem on graphs is somewhat easy because you apply the method called color coding, and when you get an FPT algorithm, solving this problem on these duals turned out to be somewhat uneasy, but fortunately we were able to adapt techniques from a recent paper. From a recent paper of Kenichi, Kawara-Abashi, and Michael Taru, and recent is really recent, and they designed an algorithm that decides whether in a given graph you can find a cut with at most a given number of edges that splits the graph in at least a certain number of components. So what we did, we basically used their techniques, which was called something like, they call it power cuts, and we adopted this technique to our setting, and when we showed that also in co-graphic Matroids you can decide the existence of a circuit containing two given edges. And I think with this short sketch of our algorithmic, of what's behind our algorithms, I think I should finish. Thank you.